right, section 1.2 is explorations with patterns. When I was in grad school, one of the things that I did research on, or one component of my research had to do with examining how people viewed mathematics. And one of the people that I had talked to defined mathematics as the study of patterns. Everything sort of could boil down to looking at patterns. And it is a really popular problem-solving strategy in some cases as well. So we're going to take a look today at solving or looking at things with patterns. So a few definition things that we're going to look at first is what a conjecture is. What we've got first going on. First, a conjecture. A conjecture is simply a statement that has not have been proven. So it's kind of like a hypothesis, right? This is what I think is happening here. So you haven't proven it yet, but you suspect that this is what's happening. Okay. Inductive versus deductive reasoning. These are two different kinds of reasoning in mathematics. And you have likely used both of them in mathematics before. You've also likely used both of them in the real world before. Not likely, you have. You absolutely have. So let's talk about the difference. Inductive reasoning is a method of taking making generalizations based on observation of patterns. So, for instance, you actually did this in the last section with Gauss's method when you said 2, 4, 6, 8, 100. So you made the generalization that the ... were a specific kind of number based on the first part of the pattern, right? And you do that as well, right? So you look outside the window and you say, lots of clouds, I should bring my umbrella, because your experience has told you lots of clouds mean it might rain. Right? So this is an observation based on what you've experienced before, and then you apply it. The other one is deductive reasoning. So deductive reasoning is the use of mathematical axioms, theorems, or definitions, or undefined terms, assumed to be true, and logic for proof. So the kinds of things you've done before with this have to do with, say, for instance, solving equations. You know from experience that it works, right? But the reason it works is not because you've just done it a bunch of times and it works. It works because there's an underlying theorem that tells you that. Something that always is true, regardless of what your experience tells you. So one of the things, we'll take it back into a non-math setting. So for instance, the Bible tells you that God loves you. Period. End of discussion. It doesn't really matter how you feel today, because sometimes, I don't know about you, but I don't feel very loved. Did you guys ever experience that? But it doesn't make it any less true. Right? The Bible tells you this, and we're done with the conversation. It doesn't matter my feelings, my experiences. Even when things go bad, and they do, right? You've got those days where like 50 million things go wrong, and you're like, seriously, something else. It doesn't change the fact that you know is true. Okay, so that's what deductive reasoning is. It's taking something that you know is true, and regardless of whatever else is telling you or going on, you know this part is going to be true and it's going to follow some different things. Okay? A counterexample is something that proves that a conjecture is false. So we created one of these in another class of mine yesterday. We did a very similar thing that you guys are going to see happen in section C, problems in your book. Some student's going to say, well, this is what I think is happening, or this is why I think it's happening, or whatever. And you have to look at their work and you have to say, are they right? And if they're not right, a really good way to show them that they're incorrect is to give them an example that doesn't work. That's a counterexample. Okay? Showing them that what they thought was going to work doesn't work in some specific case. That doesn't mean what they thought was going to work doesn't work ever. It just doesn't work in general. Do you see the difference? Okay. All right, so sequences. I think I used this word already on the board in my last class. Sequences. All a sequence is an arrangement of numbers, figures, or objects. We tend to sort of work with numbers the most, but it doesn't have to be numbers. When children, really little ones, right, kindergarten, preschool, some of you are going to work with them, God bless you. When they start working with sequences, they often work with shapes and colors, right? So we see red circle, blue square, red circle, blue square, and the question says, what comes next? It's a sequence. So it doesn't have to be numbers. But we use it as we grow up into numbers more, right? So So we see things like 1, 3, 5, 7, 9, 11, and we say, ah, this is a sequence, and I can say what the next 3 numbers are. So that's sequences. There's a couple different kinds of sequences that are numerical that we're going to look at. One of them is an arithmetic sequence. Right, so an arithmetic sequence has the sort of feature that you can take a number and add it or subtract that number from the first one to get the next one. So the ones that we did with the evens and the odds in the last section had that feature. Those were arithmetic sequences. Right, so when we go from 1 to 3 to 5 to 7 to 9, the value I add each time is 2. Right, I add 2 to get the next number. I mean, that's probably not what you were thinking when you did it, but that's what you did. I mean, really, you just added 2, you skipped a number, you added 2 to get to the next number. That number that you added or subtracted, if you were subtracting, is called the common difference. It's the value that each term to the next one differs by, called a common difference. And sometimes it's easier to work with than others. Right, so 2s are great. They can count by 2s, that's awesome. Children first start learning sequences with numbers counting by 2s. Do you know what else they count by sometimes? 5s and 10s. Those are the 3 they start with. 2s, 5s, and 10s. It's a little bit harder if you tell them to count by 3s. At least until you get beyond a certain point. They might be able to go 3, 6, 9, but then they have to stop and actually count it. Okay? But we can still do it. Right? So the common difference is the number you add to get to the next number. And I should say, one of the ways or places that you've heard that you really see this start to be developed is in the 2nd grade, 3rd grade curriculum when they start learning multiplication tables. And that is being moved into 2nd grade, folks. Yeah. Right, so 3rd grade's where I was taught it. I don't know about you guys. That's where I learned it. It is a 2nd grade topic now. Okay. So, but we start doing that, right? So the multiplication tables, we count by 3s. Multiplication tables, we count by 4s. That's how you sort of establish the whole pattern first. And eventually you have to sort of memorize those facts. But all right. So one way to express this idea of sequence is to say, I get to the next term by adding a specific number, right? So that's sort of an idea of how do I get the next number is a recursive idea. It takes the number I'm on and does something to it to get the next one, all right? So a recursive formula is a formula based on a pattern established after one or more consecutive terms are given, and the rule shows how to obtain each successive term of the sequence. It's based on what did I do to get the next one. The nth terms, so a formula used to find the nth term in a sequence when no prior terms are needed. That's a different way of thinking about a formula. Okay, so a recursive formula needs the first term to generate what's going on. An nth term formula, if you will, is more like what you did when you guys worked with equations. Right? Given an equation, it doesn't matter what number you could have had to start with. All you got to know is what's x, you put the x in, you get out a number. Right? That's more what you've sort of been doing more recently is that. This is an interesting one. Has anybody ever heard of Fibonacci? Yeah? He's a mathematician, kind of like Gauss last time we talked about Gauss, and he did some cool stuff with patterns. Fibonacci did as well. Fibonacci sequence. Now take a look at this. It is clearly not add a number and get the next one, right? That'll work. But there is a pattern here, and Fibonacci sequences occur in nature. So if you have the opportunity and you live nearby to go to the Science Museum at some point, I would encourage you to do so. They have a geometry exhibit at the Science Museum right now, and it is really cool. You might be looking at things seriously. No, it's awesome. I took a class, actually over Jason, we went to the geometry exhibit at the Science Museum. They saw other things there too. But it's really neat. They've got a lot of examples of math in nature, and it's all about patterns. I mean, primarily the math and nature stuff anyway. And so Fibonacci sequence actually has a pattern. You mentioned, remind me your name? Carrington, right? Okay. Carrington, you mentioned having seen this before. Do you remember anything about it?
I just remember my math teacher telling me that it's in everything.
Yeah, it's really cool. It is. It is. It's really cool. There's pictures and things that you'll sometimes see. Another item that's kind of like that is fractals, right? So it makes really cool pictures. So here's what you do. You add these two numbers together, and what do you get? 2, which is the next number. And if I add these two numbers together, I get 3, which is the next number. And these two numbers give me 5, and so forth. So could we go on to the next one? Sure. We add these two together. What would be my next term? 34. And we keep going from there. So Fibonacci sequence is one that always sort of jumps up and catches you by surprise because it's very specific. Number one, very specific. And it doesn't have the patterns that we're used to seeing. Okay? But if you just remember some features about it, you can see it once we do one, right? I did 2 examples, little plus signs, and you guys get 2 next. So that's Fibonacci. All right. I promise we're going to do some examples, but they're at the end here. Well, we're almost there. All right, so we talked about arithmetic sequence. I talked about this weird thing with Fibonacci, which is also an arithmetic sort of feature, like I added things together to get it. A third type of sequence is a geometric sequence. Okay? Arithmetic sequence we added to get to the next term. In a geometric sequence, we multiply something to get the next term. Now, we haven't done an example of this, so I feel like I should give you an example. So let's say that we had this, 2, and then 4, and then 8, 16, 32, and so forth. What am I doing to get to the next term? Multiplying by 2. That's a geometric sequence. A geometric sequence means I multiply by the same value to get the next one. That value I multiply by is called the common ratio. The common ratio in this particular example was 2. Right? It was 2. And we need this next definition in order to talk about that common ratio idea. So this is a definition of exponents. You guys remember what exponents are? When you raise something to an exponent, what it really means is you're multiplying it a number of times by itself. Okay? So, for instance, if we have a raised to the n, it means we have a times a times a times a how many times? N times. Now, this is sort of one of those things that you see n is a natural number. You guys remember what natural numbers are? Right, so when we say 1 through infinity, count me some. Okay, good. So the natural numbers are the ones that you first start learning when you're a little bitty. So when you first start learning when you're a little bitty, what number do you start counting with? 1. So we call those the natural numbers, which here are called the counting numbers. So it's 1, 2, 3, 4, and so forth. What that means in terms of what's going on here is that this n is telling you what happens when n is 1 or bigger, right? A whole number 1 or bigger. So I need this extra consideration down here to say, well, what happens if n is 0? Now, we're not going to talk about what happens when n is negative because we aren't working with those kinds of numbers yet. Okay? We're working with whole numbers, and whole numbers actually include the number 0. So by definition, that's how we're doing this at this point. There's other ways to go with this, but right now, by definition, a to the 0 is going to be considered the number 1. Okay? We're just going to take that as a by definition. When you get to math 2, we'll prove that that's true. Okay? All right. We're going to do some examples. Now, I've sort of described what these things are, you know, geometric versus arithmetic and whatever. What I haven't told you, though, is how to come up with what the next term is, maybe. I exactly said that. And I certainly haven't been able to tell you so far what you would do if you wanted to write an nth term formula. And you need to know that in order to do your homework. So my question doesn't exactly address all those issues, but we're going to do more than the question asks on this slide. Okay? This slide first says to list 3 terms that continue the sequence, so show me the next 3 terms. And it also says to decide if the sequence is arithmetic or geometric. Everybody with me? Okay. No matter which one you're looking at, you have to make the decision of how do I get the next term. So, first problem, how do I get from the first term to the second term to the third term and so forth? What do I do? Add 3. So, since I add 3, that tells me, is it arithmetic or is it geometric? Arithmetic. So this answers one of the 2 questions I was asked. Awesome. What are my next 3 terms? Okay, and we could keep doing this, right? But what if the question also asked me something like, find the 100th term? I don't know about you, I don't want to write out 100 terms. So I need to have some other way of finding what a general big term later on somewhere is, besides write them all out until I get there. All right, so here's the way that that works. So let's call it, well, I'll just say it this way. An arithmetic formula. This isn't precise or exact, but this is what you do. All right, so the first thing you do is you say, what number did I add everything by to get the next term? What was my common difference? 3. So you take that number. It was 3 in this case. And you use that 3 and you multiply it by whatever variable name you want to use. I'm going to use n because we called it n formula. So I've got 3 times n. So that's how you always start it. The common difference times n. After that, what you do is you put in n equal 1. Okay? So this is a trial and error kind of approach. Because I can give you a formula, but then you have to memorize the formula. No, I'm not a big fan of memorizing things when we can sort of look at it and figure it out if we need to. Okay? Too many formulas, and then you start to think that that's all math is, and it really isn't. All right? So if n equals 1, if I put 1 into that, I would get what number? 3. But I know when n equals 1, my first term is not a 3. What is it? It's actually number 1. So what would I have to add or subtract from 3 to get 1? 2. Now put in the number 1. If I put the number 1 into that, 3 times 1 minus 2, what do I get? 1, which is my first term, right? Okay, so if n equals 1, I have 3, this is sort of the check part, right? 3 times 1 minus 2, and I get 1. You need to check another one of them. I don't care if you do n equals 2 or n equals 4. We've got them all on the board. Let's just do n equals 2 because, I don't know, so we're not skipping one. Let's say number 2. So if I put n equal to 2, what should it be if I've created my formula correctly? It should be 4. Why? Because this is, oh, let me use red. This is n equal to 1, and this is n equal to 2, and this is the term when n equals to 3, and so forth. So I should be getting the number 4 if I've created my formula correctly. So let's try. 3 times 2 minus 2. What is it? 4. So the pattern is always the same. This is the pattern. And this is the whole thing we're supposed to be doing. You're not giving me formulas. The pattern. I always take the common difference, which I can find, and I multiply by n. And then I will either add or subtract some number on the end of it to get it what I really want it to be. Is everybody with me? So now that I have a formula, 3n minus 2, could you tell me what the number is for n equals 100? Yeah, good, right? 3 times 100 is 300 minus 2 is 298. Make sense? Excellent. All right. How about the next one? What do I do to get from one term to the next? It is multiply by 2. So is it arithmetic or geometric? This one would be geometric. Can you find me the next term? What do we get after 24? 48. And then 96, and then somebody said it. Yeah, it's 192. Grab a calculator, it would be okay. All right, 192. So that's actually all this question asks, right? What again if the question said find the, and I'm not going to say 100th term because it'll be too large with geometry, but let's say it wants you to find the 20th term. I mean, we could still write these out to 20. That. But I'd like for you to see how you would form a way of doing that in general as well. So this is going to be my geometric formula. All right. What was the common ratio? 2, right? The number I multiplied by 2. So I take that value and I make it the base of an exponent, which is why on the previous slide I need to tell you what exponents were, because we use them now. Okay? Now again, this number may not actually be the number I need. In fact, I need to do one more thing to it. This is just a way of handling it more easily. We don't have to have a minus 1 up there, but it's a bit easier if we do. Okay? And here's why. If I put in n equal to 1, what would this number be? What would the exponent be? 0. And what is 2 to the 0? It would be 1, right? Anything to the 0 power is 1. We did that on the last slide too. So this is the number 1. Is that my first term? No. What is my first term? 3. So on the last one, what I did is I added or subtracted a number to make it actually work out to what I want to do, right? Here, I multiply by it. But again, that should make sense because arithmetic was all about addition and subtraction. Geometric is about multiplying things together. So if I take this term now that I've got in general and I multiply it by 3, number 1, please do not multiply 2 and 3 together. That will not work. Okay, that is totally destroying properties of exponents. I know we haven't talked about them, but it is. Okay, they're not alike. One has an exponent, the other one doesn't. So don't multiply them together. It's just like it is. 3 on the outside, 2 to the n minus 1 on the inside. Now, let's check and make sure it works. If n equals to 1, so I put in here, this one right here, 3. Yeah, I realize I'm already on top of the blue, sorry. And then 2 to the 1 minus 1. So 1 minus 1 is 0. 2 to the 0 is 1, multiply by 3, and I get 3. So this gives me the 3 that I want, but I should always check one more just to make sure that I didn't sort of make a mistake. Good idea. So let's try n equal to 2. Again, it doesn't have to be 2, but let's try that one. 3 times 2 minus 1. Whoops. 2 to the 2 minus 1. What is 2 minus 1, the exponent? 1. What's 2 to the 1 power? 2. What's 2 times the number 3 on the outside? 6. Is that my next term? It was. So this is my generic form, my geometric formula. Okay, the general form for this. So now if I asked you what the 20th one is, could you do it? Yeah. You would say 20 minus 1 is 19. You'd grab your calculator and do 2 to the 19, and the number would be quite large. And then you hit times 3. Do you remember that?
Oh, yeah.
What was it?
5,244,288.
Big number, right? Considering it's only the 19th or 20th term, right? It's a pretty big number. All right, so let's actually answer this question here at the end of the slide. It says, is this inductive or deductive reasoning? So go back and remind yourself which was which on that first page. Inductive reasoning takes a pattern and it supposes more stuff about the pattern. Deductive reasoning, in essence, takes something that's known to be true, like a formula, and uses it to find something else. So let me clarify. I'm talking about the left-hand side right now. What we did on the left-hand side, was that inductive or deductive reasoning? That was inductive. That was taking a pattern and supposing if the pattern continued, what would happen next. So this over here is inductive reasoning. Now, if you have a formula, supposedly like, you have a formula given to you, right? Like if we'd actually started the problem and then it said, this is the arithmetic formula for your sequence, whatever, and then it said, what is the 5th term in your sequence, and you put that number in, that would not be inductive reasoning. That would be deductive reasoning, right? So when you have to create the formula, it's inductive. When you're given the formula, that's deductive. Everybody cool with the difference? All right, let's see what's next. Oh, all right. I'm going to jump the gun on explaining a little bit too much on the last slide. This says, find the first 5 terms of the sequence with the nth term as follows. label each as arithmetic, geometric, or neither. All right. So we're supposed to find the first 5 terms of the sequence. In essence, what I want is I want to say what happens when n equal to 1, 2, 3, 4, and 5. So, what do I get if n is equal to 1? 11, right? 5 times 1 plus 6, 11. Maybe we're trying to put an n equal to 0. That's okay. N equal 1. What about when n equal to 2? 16. What about when n equal to 3? 21. N equal to 4? And n equal to 5? 31. So let's actually write them in a list form. So this is 11, 16, 21, 26, 31. Those are the first 5. Is it arithmetic or geometric? Arithmetic, why? You add 5 every time. It has a common difference of 5. I add 5 to the next term, right? So this is arithmetic. Okay, let's do the same thing down here. Right, n equal to 1, 2, 3, 4, and 5. Alright, so if n equal to 1, I have 1 squared minus 1, which is, that's 0. If n equal to 2, I have 2 squared minus 1, which is 3. N equal to 3, 3 squared minus 1, 8. N equal to 4, I have 4 squared minus 1, 15. And n equal to 5, I have 5 squared minus 1, 24. All right, so let me write my sequence out like I did just a moment ago. I have 0, 3, 8, 15, and 24. Arithmetic, geometric, or neither? If it's geometric, you have to be able to tell me what the number is you're multiplying by between the terms. So let's pause for a second. Is there a number that you can multiply? No. And the very fact that there's a 0 and it actually makes things really not so helpful. Or maybe it is helpful. You can't multiply 0 by anything and get anything with 0, right? So it's not going to be geometric. It's not arithmetic either, right? Plus 3 plus 5, not going to work. So this one is neither. Now let me pause for a moment and go back to the last slide with you. I created something on the last slide that's actually also a really helpful thing to determine if something is arithmetic or geometric. If something is arithmetic, it has the form of a number times n plus or minus a number. It's exactly what part A here was, right? A number times n, and this one was plus a number. So it has the right form. It will be arithmetic because the form is the right form. If something is geometric, it has this form. It has a number raised to some power that's got n in it. You know, it may not always say n minus 1, but it's going to have n in that power, okay? So a number raised to something with n in the power, and then you may or may not have a number multiplied by that out front, but that's the pattern. And if you take a look on the second one, here, part B, it didn't have either of those forms, right? It didn't have a number times n plus or minus a number, and it didn't have n as the exponent of a base of another number. So it's going to be neither because it didn't follow either of those patterns. Okay, let's answer the question that's asked here in part C. Is this inductive or deductive reasoning? It is deductive. Okay, so remember what it means. Deductive reasoning means I'm given a formula, Something I know is true, I'm given this piece of information and I'm deducing something from that. Deducing, deductive. Right? That's what's going on. All right. All right, we're going to do one more example and we'll probably be done just a touch early today, so we can stop right before we make your numbers. Example number 3. All right, so I gave you a verbal description of what counterexample means. Can somebody tell me your rendition of what is a counterexample? What does it mean? Proving why something is wrong. That's a good description, yeah. You're proving why something is wrong, typically by putting some numbers in there to show that it doesn't work, right? All right, so here's the deal. We have a problem, something that a student might do, maybe something you've done in your past, I don't know. So the student says something like the following: if n is a natural number, then n plus 5 over 5 is n plus 1. Before I go finding a counterexample, which is the directions, why might someone think that this is true? What did they do to think that this was going to work? Yes?
5 over 5 is 1, but they don't think about the numerator over.
Right, so in essence, they're doing something like this. They're looking at the 5 over 5, and they're dividing. And 5 over 5 is 1. I mean, that's a true statement without a doubt. But the problem is that this really isn't 5 over 5. It's n plus 5 over 5. All right, now, from a mathematical perspective, this is actually n over 5 plus 5 over 5. And we can see where the 5 over 5 would be 1. But the 5 doesn't completely go away because the 5 is still underneath the n. Okay? That's not what the problem's asking you to do, and I don't want you to think you have to. I just want you to see what it is from a numerical perspective. It really should have happened. Now, let's think from a, a teaching perspective. We've got the student, and the student has made this error, and you want to tell them a counterexample. All right? So just from a perspective of the teacher, the first thing you might tell them is, you did something right. You understood the 5 divided by the 5 would give me a 1, and so you're thinking right, but not exactly for this problem. The difference on this problem is, I don't have 5 over 5, right? And maybe you break it apart like I just showed you, but at the very least, you could show them why it doesn't work with some numbers. Now you have to be a little bit careful because you might pick numbers that actually make it work. If you picked the number 0 for n, it would work, wouldn't it? If that were the case and it worked, you'd say, okay, step back, let me pick another number. Somebody pick me another number for n. 5. Okay, let's say let n equal 5. So if n equals 5, I have 5 plus 5 over 5, and I want to compare that to 5 plus 1. So, order of operations, or however you think of it, what is the 5 plus 5 on top going to give me? 10, and 10 divided by 5 is 2. So this description right here is actually equal to 2. I don't want that there. That looks like an 11. So this is 2 on the left-hand side. And then 5 plus 1 is 6. And we can say clearly 2 does not equal to 6, right? So there was an error in what you did. This idea of sort of being able to cancel the 5s and the 5s, which I have students tell me quite frequently in college that you can still do that. Work like that, okay? You will get work like that too if you teach anything probably in about 4th grade and above. Somebody's going to do this and you're going to have to tell them why that doesn't work. And this is an example of a counterexample to show why it doesn't work. Make sense? All right.